This is a video to help explain bin radii, bin allowances, and how it affects your design. Now, in front of us we have a bracket of some sort, okay, and this is in its final shape. This is how it would actually be sent to wherever it needs to go to be used, okay. Now, often things such as this, brackets and chassis, they actually start off flat, and the designer or drafter actually draws a flat pattern, and then the machinist or manufacturer actually, after they punch out or cut out the desired holes and slots, they actually bend it to get it in the final shape that you see here, okay. And you can see that there are a few bends in this one. You see at the corners in the back, and then this part here, okay, on each side is bent as well. Now we'll switch over to a detail sheet to show you what a detail sheet would look like in this case, and you can see that you have a top, front, and right side view of the object as its final configuration, so to say, okay. And you have some notes here about the object, and what you have here is a flat pattern layout of the bracket as it would actually be cut out or manufactured. And you can see here that there's some lines, and these are delineating where the object will be folded. Now, you would think it would be fairly simple to get from here to here, but there is some intermediate steps, and the reason is, if I go back to the 3D model, when you start off with a flat pattern, and especially when you get into metals or thicker metals, and your tolerances are more important. And when I say tolerances, these slots and these holes have to line up or mate with other objects, and they have to be in an exact place in a lot of cases, okay. So taking that into account, and also taking into account the fact that the object is undergoing physical changes when you bend it, okay. So there's a lot of things to consider to get from a flat pattern to an actual 3D object. And if you think about it for a minute, this object originally was straight up and down, okay, and it was folded into the position you see here. During the folding process, this outside surface was undergoing tension, and you could see that fairly easily, like if you took a stick of chewing gum, for example, and bent it, and you could see the gum pulling apart on the outside because it's undergoing tension, okay. Now the opposite is going on underneath. That part of the object is undergoing compression, okay, and this actually deforms the object, and these parts that you're concerned about being in a certain place may move, okay. So what you actually have to do is take all this into account when you're doing your flat pattern, to make sure that when it's bent, everything is in the correct place, okay. Luckily, there's a neutral axis between the tension and compression that doesn't experience any forces, okay, and that's what you work with. And probably the easiest thing to do is switch over to a simplified representation, okay. And what we have here is just an object, a flat object that was bent at 90 degrees, okay, and you can see the different parts of the object called out, like the thickness, the bend angle, the bend radius. By the way, this is the inside surface. It's always on the inside, okay. And here you see the neutral axis, and this is the part I was talking about that's not undergoing any tension or compression. Now you also see this K value, and the K value, it's not set in stone. There is no one K value. It depends on a lot of factors, such as how thick the material is, the type of material, even the grain of the material, okay. It depends on a lot of things, and a lot of times this K value is actually experimental in nature, and someone actually through trial and error determines the K value. Now and in any cases in class, I will give you the K value, okay. But there are a couple of things that you should know about the k-value. For one, it can't be more than 0.5, and it can't be less than 0.25, but it can be anywhere in between, and like I said, it depends on the previously described factors. But what you want to find out through the use of the k is the length of the bend allowance, okay? And this is what you actually use to determine the total length of the object as it's folded, okay? So you would add the length of this plus the length of the bend allowance plus the length of this to determine what the final shape would be, okay? And you can use it on more complex shapes. You don't have to use it on just simple shapes like this. You could use it on objects like this, for example, okay? Before we get to that, though, there's a fairly simple formula that you can use, okay, to determine this. Now, this L is just the length of this bend allowance, okay? Now, it may look complex, but it's really just a matter of plugging in numbers, okay? R is the bend radius that we discussed already, and I'll either give that to you or you can click on your properties when you do your problems to determine your radius, okay? Your k value will be given to you, and your t is your object thickness, and you multiply that inside the parentheses times 2 times pi times a, and the whole amount divided by 360, and that will give you this length, okay? Now, if you need to determine your total length, which ultimately you will, you need to add this length here plus the length of the bend allowance plus this length here, okay, to get your total length. And when we come back in the next video, I'm going to work through a sample problem to show you exactly how to do that and why you need to do it. And that concludes this video.